Alright, today is officially the start of spring, the vernal equinox, the spring equinox, March 20th, whatever you want to call it. But because of that, I figured it'd be a good day just to dive into the science of why we have seasons. So just looking at this picture right off the bat, you can see we have the sun and we have the earth orbiting around the sun. And the reason we have seasons is really due to two things. The fact that we do orbit around the sun and the tilt of the earth's axis. The reason the tilt is so important, for example, without the tilt, we wouldn't have seasons. The reason the tilt's so important is because it changes our length of day, and then it also changes how direct the sunlight is going to be. So to understand this, let's just look at the summer solstice first. And let's think about light coming from the sun is only going to hit the half of the earth that the earth is facing. So that the earth is facing, I don't know if that makes sense, but basically, if you look at what part of the earth is in darkness, it's the majority of the southern hemisphere on June 21st. More of the northern hemisphere is pointed towards the sun, so the day is going to be longer. It's going to be spend a longer amount of time spinning in the sunlight, and you can actually see the northern hemisphere is going to be in the sun's rays all day long. That's why on the summer solstice, and actually the 6 months of the year where the northern hemisphere is pointed towards the sun, the north hemisphere has 24 hours of daylight. Now the other aspect is the sunlight coming from the sun is going to be a lot more direct in the northern hemisphere, whereas it's going to be hitting more obliquely in the southern hemisphere, or less direct. That might be a better word there. So now let's look at the winter solstice. This is December 21st. The exact opposite is going to happen. If we look at it and erase the part of the earth that's in the dark, you can now see that there's that little sliver of the southern hemisphere that is now showing up, and the North Pole is in complete darkness. So it's this 6 months of the year that there is no sun on the North Pole. Now the other thing that would happen is the northern hemisphere would have a shorter day right here because as it's spinning around, it's in the sunlight for less of that spin. And then the sunlight is also going to be hitting more directly in the southern hemisphere and not as directly in the northern hemisphere. So that's still, and then the autumnal equinox and the vernal equinox, that's where the tilt doesn't matter as much. It's just equal days because the sunlight is spread out evenly over the surface. So almost everywhere has a 12-hour day on the autumnal and vernal equinoxes. So, and that's why there's more mild weather. So that could still be a bit abstract. So now let's break down a little metaphor that I think will help explain this concept a little bit better. So let's think about two flashlights right here. So, yeah, those are flashlights. I'm not the best drawer, but it'll do. So this flashlight is pointed directly at the surface right here. And it is going to make a very bright, small circle. Whereas this other flashlight is pointed a lot more obliquely. So it's going to make a much larger circle. If you think about it, it's going to come in like this, and this circle is a lot more of an oval. Oops. So how you could think about that is, if my drawing's not great, you can just think about if you were to shine a flashlight directly at a wall, it would have a very small bright circle, and then if you tilted it up the wall, it would spread out a lot more. And as it spreads out a lot more, you have the same amount of light being spread out over a larger area, so the intensity of it goes down. That's exactly what's happening. So northern hemisphere summer, you can think of as that flashlight that's hitting directly. During the winter, you can think of it as that sunlight coming in at a very oblique angle. So just to draw that another way, just in case that doesn't make sense, let's go in and actually look at the Earth again. So when the sun is right here, it's going to be hitting very directly onto the Earth's surface, close towards the equator, and you can see how much space that is going to take up. So that's our direct flashlight right there. Now when the sun is up here, let's try to draw our little lines in. Okay. And it's going to go all the way up there. Now, that's the space that same initial light is now being spread out over. So what that means is that when the sun is more direct, the intensity of the light's going to be stronger. When the sun is more oblique, that's where the intensity is going to go down. So that's part of the reason that the equator is hotter than the North Pole, but it's also part of the explanation of why when the Northern Hemisphere is tilted towards the sun, that sunlight is coming in at a more direct angle, so it feels hotter, whereas when the Northern Hemisphere is pointed away towards the sun, it's less direct sunlight and it's going to be colder. So, final way we can draw this is looking at this weird little compass thing that I've drawn. So, north is to our right, south is towards the left. So this is looking at the Northern Hemisphere throughout the year. So what's going on here is that sun that's more overhead, you could say, is the June sun. That's June, and this is December. So let's think about what's going on here. That green is supposed to represent the Earth. We have our little city right there. During summer, the sun is going to be a lot more overhead in the Northern Hemisphere. So as the light comes down, it's going to be very direct sunlight. Whereas when the sun is way over here in December, it's going to be more that oblique angle, and it's going to be a lot less intense. So that's the basic idea behind this. It's the tilt of the Earth's atmosphere. If you're tilted towards the sun, your days are going to be longer and your sunlight is going to be more intense. When you're pointed away from the sun, your days are going to be shorter and the sunlight is going to be less intense. Now, I didn't exactly explain why that really happens. The reasoning behind it is when you're pointed away from the sun and your sunlight's less intense, that sunlight is not only spread out over a longer area, but it also has a longer path through the atmosphere. As it has a longer path through the atmosphere, it's going to be bouncing off of more particles that leads to more scattering and absorption, and you're just going to lose some of that radiation and that energy from the sun. So the more direct path, the shorter the path through the atmosphere and the more direct it hits. The longer the path, like through a winter atmosphere, that's going to lead to more scattering, and it just makes the sunlight less intense. So hopefully that was helpful. If you have any questions, let me know in the comments, and I'll try to answer them in future videos. Thanks for watching.